In this recording, we're going to be looking for an example of a commutative ring that is not a field, but has no non-trivial ideals. Now, I ask you to do some preparation work before watching this video, and I want to start by reviewing what I ask you to do. And the first thing is I ask you to think about 3z. Now, 3z is the principal ideal generated by 3 inside the set of integers. So 3z is a ring. The second thing I ask you to do is I ask you to think about 9z. And 9z is also a principal ideal of the integers. It's generated by 9. But in particular, I ask you to think about this. I ask you the question, is 9z a subset of 3z? And the answer is yes, and the reason why is pretty simple. If x is inside 9z, then x looks like 9 times k, and 9 times k can be rewritten as 3 times 3k. And since 3k is certainly an integer, this definitely lies inside of 3z. Now, the upshot of both 1 and 2 means that we can actually say that 9z is actually an ideal of 3z. It's certainly a subring because 9z is a ring, and 9z lives entirely inside 3z. And also, we've got the superclosure that we need for an ideal. If I take x inside of 3z and y inside of 9z, then what I know is that x is equal to 3 times L, and y is equal to 9 times k for some integers L and k. And so what this says is that xy will be 3L times 9k, and that would be 9 times 3LK, which is certainly in 9 times z. And because we're in the integers, y times x and x times y are the same thing. So this says 9z is an ideal of 3z. Now, the reason that's important is that says 3z mod 9z under coset addition and coset multiplication is a ring. And it turns out that this ring will be the ring that we're after. So let's start working on that. The first thing that I want to do is I want to think about what are the elements of this ring that I'm going to call R, which will be 3z mod 9z. Well, a typical element of a quotient ring looks like something in the original ring, and the elements of 3z look like 3a. Plus we have the ideal. That's the typical element. This is a typical element of my ring R, which is my quotient ring. Now, we also know that in quotient rings, each of the elements has multiple ways of being represented. So I want to also address that question. When is 3a plus 9z equal to 3b plus 9z? Well, we know the answer to that. Two cosets are equal if and only if the difference of their representatives belongs to the ideal. So we would have 3a plus 9z is equal to 3b plus 9z if and only if 3a minus 3b is inside 9z. But we can go further. This is saying that 3 times a minus b has to be inside 9z. And the only way 3 times a minus b can be a multiple of 9 is if a minus b is a multiple of 3. So 3 times a minus b is inside 9z only when a minus b is equal to 3q. In other words, this is true if and only if a and b are congruent mod 3. And this lets me actually explicitly write the elements of my ring R very nicely. There are only 3 equivalence classes mod 3, and so what this says is that our quotient ring can be thought of as 3 times 0 plus 9z, 3 times 1 plus 9z, and 3 times 2 plus 9z. Because the only choices for A and B mod 3 are 0, 1, or 2. But we can clean this up. 3 times 0 is equal to 0, so we have 0 plus 9z. 3 times 1 is 3 plus 9z. And then 3 times 2, that would be 6, and we have 6 plus 9z. So in particular, our ring has exactly 3 elements. And that's going to be relevant because we could use this and Lagrange's theorem to actually show that R has no non-trivial ideals. So let's think about what Lagrange's theorem actually says. Lagrange's theorem says that if we have a finite ring and we have a subring, and all ideals are subrings, so I can think about it as an ideal of R, then the number of elements in I has to divide the number of elements in R. So since R equal to 3z mod 9z, has 3 elements, if I is any ideal of R, then it turns out that the size of I has to divide 3, so that means the size of I either has to be 1 or the size of I has to be equal to 3. Well, if I only has 1 element, then I is just the 0 divisor. And if I has 3 elements, I is the whole ring. And so that says 3z mod 9z has no non-trivial ideals. Well, we have one last thing that we need to figure out, and that's is R equal to 3z mod 9z a field? Well, we can investigate that by looking at the multiplication table for this ring. And here's what the multiplication table looks like. We have 3 elements, 0 plus 9z, 3 plus 9z, and 6 plus 9z. And of course, we have those same 3 elements for the rows. And now all we have to do is do the multiplication. And the multiplication is actually pretty easy. All we have to do, since we're in a quotient ring, is multiply the 2 coset representatives together and basically reduce modulo the ideal. So we have 0 times 0 plus 9z. We have 0 times 3 plus 9z. We have 0 times 6 plus 9z. We have 3 times 0 plus 9z. We have 3 times 3, that's 9 plus 9z. But 9 plus 9z is the same thing as 0 plus 9z, because 9 is congruent to 0 mod 9. And 3 times 6 would be 18 plus 9z, but that again is going to be 0 plus 9z. And 6 times 0 is 0, so we have 0 plus 9, 0. 6 times 3 is 18, so we have 18 plus 9z. And finally, 6 times 6 is 36 plus 9z. But again, 18 plus 9z is the same as 0 plus 9z. And 36 plus 9z is the same thing as 0 plus 9z. And I want to make sure that you remember why. 9 plus 9z is the same thing as 0 plus 9z, since 9 and 0 are congruent mod 9. Likewise, 18 plus 9z is congruent to 0 plus 9z, since 18 is congruent to 0 mod 9. And finally, 36 plus 9z is the same thing as 0 plus 9z, since 36 is congruent to 0 mod 9. So what this means is that this particular multiplication table, when we stare at it, boils down to this table. We have 0 plus 9z, 3 plus 9z, and 6 plus 9z. And same thing for the rows. But the answers are always going to simply be the 0 inside the ring, because the 0 inside this ring is nothing more than 0 plus 9z. That's one of the things that we know about quotient rules. And if we look at this particular table, it becomes clear that 3z mod 9z has no multiplicative identity element. Hence, 3z mod 9z cannot be a field, even though its multiplication is commutative. And that completes this video.